thing you got to realize is that in casting between the types of unsigned and signed entities, the bits don't change. Just the interpretation of what the bits means changes. So going from a two's complement integer to an unsigned integer, you maintain the exact same bit pattern and you just reinterpret what it means, right? Same thing going from unsigned to two's complement. You don't change any of the bits, you maintain the same pattern, you just reinterpret what the bits are supposed to be meaning. So if we look at a simple example with just 4 bits, instead of having to deal with like 32, which is the actual size of an integer on the computer, if we just had a 4-bit integer, it was a signed quantity, then you could represent the numbers from 0 to 7 in positive numbers. You can't represent 8 because you can't use that bit for a positive number. That bit would mean that it's a negative number, right? So if you're just looking at the combinations going up, as soon as you get to this combination, 1 and all zeros, that's the number -8. It's the most negative because if you think in terms of this bit on the left representing that -8, and then you subtract 0 from it. You think of that bit as representing -8, you subtract 1 from it. So as these numbers get bigger in the rightmost 3 bits, you're getting closer and closer to 0, right? So the -1 is all 1 bits. The 8 minus the 7 gives you the -1, right? So you see how the thing works. Now, if you are thinking in terms of these are the signed, if I'm interpreting these bit patterns as two's complement signed stuff, those are all positives and those are all negatives. If I reinterpret the same bit pattern just as an unsigned, then it's just the big magnitudes, right? So if I reinterpret -1 from a signed quantity, I would get 15 as what I would think that meant as an unsigned quantity. You see, the bits don't change, just the interpretation. So then we go to this one. And this is just trying to show you that the large negative weight, that leftmost bit, right, when it's a two's complement thing, becomes a big magnitude if you interpret it as an unsigned quantity, right? That large negative weight becomes a large positive weight when I'm reinterpreting it from a two's complement to an unsigned, right? So far, so good? All right. Well, let's look at this little diagram here. Whoop. So if I start with my T max means two's complement maximum positive number I could have. The T min is the two's complement smallest thing I could have, the most negative thing I could have. So 0 going up to these positive numbers, they all line up the same if I reinterpret it as an unsigned. But if I take these bit patterns down here and I reinterpret them as unsigned entities, the -1 is all ones. So that's the biggest unsigned number I could have, right? The unsigned max. Does that make sense? So you see it kind of flips upside down here or moves, shifts that over there. Reinterpreting the encoding from a two's complement to just an unsigned, you get that kind of effect, right? The negatives become big positives. And the more and more and more negative away from 0 they get, the more closer and closer and closer to 0 they get here as positive values. So when you write a constant down in a C program, if you just write a bunch of numbers, he's going to assume that you're writing a signed quantity, something that's stored in two's complement that could, be in an integer. The integer type, int, is a signed type, can hold positive and negative values. If you want to write a constant down and say, oh, this is an unsigned value that I'm giving you, you put the U after it. Then we deal with casting from one type to another. If I had two integers, tx, ty, t meaning two's complement, right? And I have unsigned ux, uy, the way you do a cast in C is you write the type that you're casting to inside parentheses and you stick it up against the thing you want to cast. So this would be casting an unsigned to an integer. See, this is the integer dx. Now, the thing to remember is, of course, when you cast from unsigned to signed, the bits don't change. You're just going to reinterpret how you interpret the bits, right? So you just pick up the bits that are here and stick them in this other variable. You don't change them. Same thing for going from signed entities, two's complement things, to unsigned, casting it into this unsigned variable. The bits don't change. You just pick it up and put it in there. And then when you use it in these variables, in these contexts, you would use it meaning whatever those bits mean as an unsigned quantity or whatever those bits mean as a two's complement quantity. Now, the reality is in C, you don't ever have to do this int and unsigned business to go from an unsigned to an int or an int to an unsigned because he implicitly does it for you. So this is the same exact thing as up here. You just don't write the cast. The cast happens implicitly. It just picks up these bits, sticks them in there, picks up these bits, sticks them in there. And he doesn't care that these types aren't really the same. It's an implicit typecast. C has a big monster table in the book about all these typecasts and which ones, what happens when it does these implicit typecasts. You just have to memorize the book, the table. So the simple ones here, the unsigned and signed quantities, they just pick up the bits, stick them in there, right? So what does it matter, you ask yourself? Well, let's look at some examples. If you have a mixed mode expression in C, that is, I have an expression that contains some things of one type and some things of another. And specifically in this example, we're looking at mixed mode expressions that contain both unsigned quantities and signed quantities. Then what happens? How does it deal with that? Well, the rule, which is slightly counterintuitive in C, is that it's going to take all the signed values and implicitly cast them to unsigned values. So this includes when I'm doing things with all the comparison operators, right? If I had a unsigned thing and asking if it was less than some signed thing, then it's going to convert the signed to a context of unsigned and then do the comparison. So you might get some things that you don't expect to get, as we'll see in a second. Here's a constant zero and an unsigned constant zero. Well, those are the same thing, right? But all zero bits. This is the equal, logical equal operator. The single equal sign is the assignment operator. So they use two equal equal for the logical comparison of equality. And so if you were to ask, does zero equal unsigned zero? The answer would be, yeah, it does, right? Now, what if you're doing this comparison operator and you have -1, which is a signed quantity, right? And you're asking, is it less than 0? What's going to happen? Well, this is mixed mode, right? This is signed, no, I'm sorry. This is signed and this is signed. It's not mixed mode. So -1 less than 0 is going to be true. However, look at the next one where you have a mixed mode expression of -1, a signed quantity, and an unsigned quantity, and you're asking greater than in this case. This is all 0 bits. What is -1? It's all 1 bits, right? And the rule is when you have the mixed mode expression, unsigned and signed, it cast the signed one to an unsigned. So it's going to interpret this bit pattern of all ones as if it was an unsigned entity, which is the biggest unsigned number you could have. That's U max. It's all 1 bits. So it's going to be greater than 0U. Not quite what you might have expected, right? Because the signed quantity got reinterpreted as an unsigned quantity in the mixed mode expression. Question about that? Sleight of hand trick there. So if I said if minus 1 greater than 0U, the unsigned 0, the answer would be true, right? Does everybody see why? Now, the example is giving us the fact that in a 32-bit word, the T-min, the smallest negative number you could represent, decimal, is this monster here, right? And the T max is that guy there. Notice the plus or minus 1 thing, right? The minus range looks like it's 1 more than the plus range, but the plus range includes 0. So they have the same number of values in the minuses and the net positives, right? So that's the smallest thing. So in 32 bits, this number minus blah, blah, blah in decimal looks like what? It looks like all 1 bits, right? I'm I'm sorry. It looks like a 1 bit followed by all zeros. Go back to here to see that, right? The smallest T-min, right, looks like a 1 bit followed by all zeros. Minus 1 is all 1 bits, right? So if we go back to the slide we were on, and we look at this value here, T-min is going to look like what in 32 bits? A 1 on the left and 31 zeros to the right. That's our T-min value for this size word. T-max is going to look like what? 0 followed by all 1 bits. Can't use the leftmost bit for magnitude, right? Because it would be meaning a negative number. So if I look at this number here as a signed quantity, the one with the 67, that's my T max. That's a 0 with all ones to the right of it, right? And I look at this guy, minus blah, 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 blah. He's got the 7 minus 1. Well, that's this number here. That's my T min, right? So what does T min look like? T min looks like a 1 followed by all zeros, right? This is a 0 followed by all ones. This is a 1 followed by all zeros. And these are both signed quantities, right? They're not unsigned, so there's no mixed mode thing going on here. So if I say, is this greater than this? The answer is going to be true. But watch this one. This is this number as an unsigned, right? And this is, which is going to be what? Is going to be a 0 followed by all ones, right? Because of that. And this is my T min, the thing with the 8, right? So that looks like a 1 followed by all zeros. This is a 0 followed by all ones. This is a 1 followed by all zeros. And I have a mixed mode expression. This is a signed quantity. This is an unsigned quantity. So when I do this less than comparison, it's going to cast this one as an unsigned. And it's going to say, as just magnitude form unsigned thing is a 0 followed by all ones less than a 1 followed by all zeros? And the answer is going to be yes. Does everybody see why? So when you are learning these things, the way to do it is you write little short pieces of C code, right? And here's our int I and our unsigned int u, right? And just like in the example here, why is that being a pain? Okay. In the example, we're going to put this number, the blah, 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 unsigned thing. There's our u, meaning unsigned constant, right? Sticking it into the unsigned variable. Here's our integer, and we're going to put this thing in that integer. So now we've got the thing set up, and we're going to print it out in hex, in 8 hex positions. That's 32 bits, right? To see it in hex, and then we're going to print it in decimal, both cases. And then we're going to have an if statement. If u is less than, which is the thing we're doing here, right? If u is less than the I, print true, else print false. So I'm gonna do my Alt X compile thing, and I'm gonna compile this file, put it in a.out, everything worked. So now I'm gonna run it, Alt exclamation point, and the command I want to run is a.out, and here's the output. So when we print the I, which is this one over here, in hex, see it's an 8, which is 1 followed by all zeros, right? Because that's my T min number. T min is always a 1 followed by all zeros. And when I print the unsigned, this guy, I get a 0 followed by all ones. That's that number, right? So if I do the comparison, it's mixed mode, so it's going to cast the integer to an unsigned, right? And saying, just looking at it as a magnitude, as a unsigned quantity, oh crap, I'll get it back for you. Just looking at it as a quantity, that 1 followed by all zeros is bigger than 0 followed by all ones. So I get true. Make sense? What's going on? You got to know the rules. Mixed mode expressions with unsigned and signed quantities, it casts the signed ones as unsigned. Then it's going to do the equality test, the comparison, less than, greater than, those kind of things, right? What about this one? -1, that's a signed quantity, a two's complement thing, right? That's a two's complement signed thing. So there's no mixed mode business going on here, right? And I'm saying, is -1 greater than -2? What am I going to get? True. Now I have the -1 and I cast it as an unsigned, which makes this a mixed mode expression. Have an unsigned thing being compared to a signed thing. So it cast the -2 as an unsigned, right? -1 has all 1 bits. So he's, as an unsigned thing, the biggest thing you could possibly have. The -2 is all one bits except the rightmost one is a zero. So this minus one, unsigned, is bigger than the minus two. That's true. Does everybody see the strange thing that's happening here? We're awful quiet this morning. Doesn't give me a warm, fuzzy feeling, getting no feedback that you actually are understanding what we're talking about. Is there any questions you want to ask about this crazy stuff? Mixed mode? Okay. Well, the way to do it is always use the computer to learn how to use the computer, right? I mean, he's the ultimate arbiter of how does this work? It's run it on the computer and see how it works, right? So the thing to do is to write these little short test programs that you can just set up something, from the example and then run it on the computer and see what it does. That's the way to learn it. Okay. So I will gin you up a bunch of examples of this kind of stuff, and then you can run it and make sure you understand why it's doing what it's doing. So this kind of stuff, I've told you before that programming in C is, the training wheels have been taken off and there's all these little gotchas you got to watch out for. And you got to really understand what the rules are and understand what's going on, or you can create all kind of bugs and all kind of security flaws in your code. And so here's a famous example of this mixed mode stuff creating a security flaw. Where's Have a little simulated example here. This isn't really the way this would actually look in the OS kernel code, but the idea here is that, okay, suppose I'm writing some stuff up in the operating system kernel, and I have this little function that I'm writing. And what this function is supposed to do for me is copy some stuff out of a hunk of space, a buffer up in the kernel down into the user's address space, like maybe giving him he asked me to read a block off of a file or something. So I went and got it, dumped it in a buffer. Now I need to take that buffer and I need to shove it down into the user's address space into the place he told me he wanted me to read it into or whatever, right? So I'm returning a chunk of space from the kernel down into the user's address space. And here's the little function I'm going to use to do it. So I have int copy from kernel void star, which is your sort of money laundering address, right? It's an address, but I'm not saying what type of thing it points at, right? Just send me any old generic address in here. And that's the destination address in the user's code where I'm supposed to copy the results to. And then we've declared this character buffer 1K big, 2 to the 10th, right? So I got 1K of space in this little array, this buffer, and I'm going to copy things out of that into the user's address space here. And so the copy from kernel has the pointer into the user's address space where the thing is supposed to get copied to. And then it has this integer here called max length. And the idea is if you call the copy from kernel guy and you give me something that's bigger than the k size, the size I've declared, I don't want to copy, you know, 2048 things out of a buffer that's only 1K big, right? So I want to have this statement in here to make sure that if you give me something that's bigger than the size that I declared the array, that I only copy the size that I declared the array, right? So that's what this statement is supposed to do. So to understand this statement, we have to understand this new operator we haven't seen in C, the little question mark guy. And this is just a shorthand way in C we have of writing an if statement when there's only one statement in the then part and one statement in the then part. It's just too much bother to do all that if then else type stuff, right? So we have this little shorthand thing. Here's the condition of the if statement. And if that's true, this is the then part, do that. If this is false, the thing after the colon is the else part, right? So if k size is less than max length, produce k size and shove it in this variable. If k size is not less than max length, produce max length and put it in the variable. So what this statement is supposed to accomplish is if you give me a max length that's bigger than the declared size of the array, I only want to copy the size of the array, right? Because I can't, it's a security flaw. If I walk off the end of this array and start grabbing chunks of stuff out of the kernel, shoving them down into the user's address space, you may be able to see things you're not supposed to see, like somebody's password or whatever, right? So it's not a good thing to shove things into the user's address space that they're not supposed to see. I'm only going to give you this buffer. So that's what this statement is supposed to be accomplishing, right? And the way it does it is it, does this little test and then it puts either the declared size of the array or how many you ask for, if that was smaller than the declared size or equal to. And then it calls this function called memcopy. And you hand memcopy the address you want to copy the stuff to, the address you want to copy the stuff from. And remember, when you write the name of an array down in C and you don't give it a subscript, it means the address where that array begins in memory. So that's the pointers are kind of the same as arrays business. And then this is the length, how much you want to copy. So copy this many bytes from here to here. But there's a security flaw. Then it returns how many bytes you copied as a result of the mem copy, or the copy from kernel. So can anybody tell what the flaw is in this code? It has to do with this mixed mode stuff, integers and unsigns. Well, it turns out if you go do a man page on memcopy, this variable length here in memcopy is declared as an unsigned, not as an integer. So what would happen if I called copy from kernel and I handed it -1 as the max length? Well, let's see what would happen. Here's this comparison. Is -1 bigger than the declared size of the array? No. So what's it going to do? It's going to take this max length and put it into length. So now I've got -1 sitting in the length. Now when I call memcopy, the -1 goes in, but in memcopy, that gets interpreted as an unsigned, which is all ones, which is U max, the biggest possible unsigned thing I could possibly have. So when he copies the stuff out of the kernel, he's going to walk right off the end of this array and grab whatever in memory is sitting there, just huge amounts of it, and copy it down into the user's address space. So that's a security flaw, right? There's a bug in there. And it's because it's declared as an int here and used as an unsigned here in the function that I'm calling. So it casts the signed thing to an unsigned. And now that negative number looks like a big monster positive unsigned number. Does everybody see what the flaw is? How it results from this casting of the signed to the unsigned? So when we write Unix and Linux and all these things in C. That's what we write them in, the kernel. And we do that because it's a language designed for doing that kind of thing where we can get down and dirty and just grab the computer by the throat, reach into memory and move things around, do whatever we want. That's the kind of language we want for writing an operating system. But it also comes with a lot of baggage, all these little security issues of the way it's designed. So there's a lot of little fast and loose, loosey goosey kind of things going on when you write C code that'll bite you if you're not paying attention. And so that's the reason that you keep seeing year after year after year discovering more and more and more security holes in the TCP/IP implementation or in the kernels of the OS or whatever. It's because of these little insidious types of things. So there's a similar flaw in the FreeBSD implementation of the get peer name, which is a call that you make when you have a TCP connection and you want to get the name of the computer on the other end that's connected on the TCP connection. So there are legions of smart people trying to find vulnerabilities in programs and ways to exploit them. Because they don't have a job and they have nothing better to do than to sit around and do that kind of thing. Okay. Questions about this security hole. So this is just trying to show you that if push in a minus thing in there, right? It's going to get interpreted as an unsigned, which looks like a really big number as an unsigned. And that's the basis of the security flaw. So in summary, when you cast signed to unsigned or unsigned to signed, nothing happens to the bits. They don't get changed. You just reinterpret what they mean. And that can have unexpected effects because of that leftmost bit either representing as an unsigned a big positive quantity or that leftmost bit in a signed entity representing a big negative value, right? So that's the crux of the issue. So expressions containing signed and unsigned ints, the int is cast to an unsigned, which is usually not what people think would happen. Any questions? Well, if not, let's look at some example code I have for you to play with. I'll put this out on Canvas. I can find it. See where I put it. Okay, hang on. Let me find my example code here. Okay. So I'll go back over here. And I want to open another file. So here's a little hunk of code that I concocted with a bunch of these examples of our bit level operators just to make sure everybody's cool with that. So I've got our friend 41 hex in A and 0 in B, right? And then what's going to happen when I do the logical operation A logically ANDed with B? Well, A is 41 hex, right? From C's point of view, anything with any 1 bits in it is true. So A is going to be interpreted as true. B is going to be interpreted as false. And so A and B is false. So the result of a logical operation is always either the number 0 or the number 1, and 0 means false. So this is going to produce 0, right? So if we compile this thing, and so if you don't tell him where to put it, he puts it in a file called a.out. So we can run the a.out file and do an alt exclamation point in Emacs to run a shell command. And the shell command I want to run is a.out. So if we run it, for example, 1, you see this little 0 coming up here as the result. This business right here, right? That's the result of that operation there. Now the second one takes the A and the B, still have the same values, and it does the bit level AND of A and B. That's the single AND operator. So when you do the bit level AND, it pairs up each bit position and says, are they both 1 in that position? If they are, there's a 1 in the result. If they aren't both 1, you get a 0. So you're ANDing with 0. So that's just going to wipe out everything in the result, and you're going to get, in example 2, you're going to get 0 again for the bit level AND, right? What about example 3? Now we put 7 into B. So we got 41 hex in A, 7 in B. We're doing a logical AND. 41 looks like true. 7 looks like true. So this overall thing is going to be true. The result of a logical operation is always 0 or 1. True is a 1. So we ought to get 1. Oops. Example 3, 41, 7. The result is 1, right? Questions? The next one, we're going to do the bit level AND of 41 hex and 7. So if we line up all the bits in 41 hex and 7, the only one where there's 2 ones in the same position is the very most rightmost one. Because what is 41 hex? It's 0, 1, 0, 0, 0, 0, 0, 1. And this is 0, 0, 0, 0. So none of those 1 bits in that 4 come through, right? And the 7 is 0, 1, 1, 1. But this is 0, 0, 0, 1. So the only one that lines up is the rightmost one. So we're going to get 1. So when we ANDed the 7 with the 41 as a bit level AND, we got 1, just like we did when we did the logical, but for a completely different reason, right? Now, here's our mixed mode thing we were playing around with, right? So this ends up being true because it's going to cast the int as an unsigned. The int happened to be tmin, which is all 1 bits, right? So that looks bigger than that unsigned quantity. So I get I, this negative number, being bigger than that. Counterintuitive, but you see why, because of the cast. So I haven't put these files out on Canvas yet, but I will stick them up there this afternoon. Give you an announcement. Any questions about this craziness? It's slippery, right? But you can understand what's going on, right? Just step by step, see what its rules are for how it's interpreting these things. So, this is the way to teach yourself, or if you're unsure about some particular problem, put it on the computer and see what the computer does, right? That's the ultimate arbiter of how does this work on the computer, right? So that's the way to learn any programming language or anything really on the computer. Do it on the computer. So your lab today, if your lab is today or later this week or whatever, is an introduction to some fundamental C programming concepts. And the way you should do your lab is you should bring up the tutorial, which is a web page that I've written. It's got all this stuff in it. Back to the beginning of this thing. So it's this tutorial. Um, that has all these topics in it about C programming. You work through all these different topics or whatever. But while you're doing it, you shouldn't just read this like you're reading a short story or something. You should have a terminal window open over on Schofield, and you should have an editor going of some flavor where you're actually typing in the examples that you're working through and compiling them and running them over there. That's how you learn, right? So that means we need to know how to use at least some flavor of editor on Schofield. And there are a bunch of them. If you go to files, handouts, there's a file in there called editors on Schofield. And there's a whole bunch of different editors that you can run over on Schofield. The two common ones that people use most in the Unix world are Emacs, VI, but there's all these other ones too. And I don't know, for some reason, editors tends to be like, you know, what kind of clothes do you like to wear? It's just a personal preference kind of thing more than anything. And so you can try test drive these guys and find one that you like. Um, you don't really have to learn anything other than two commands to be a novice running Emacs. You have to learn that Control X, Control S saves your file. Control X, Control C gets you out of the editor. Everything else is move the cursor around and type things in, and you can delete with backspace or the delete key. So I mean, that all you need to know to survive. But um, if you want to run some of these other editors, that's cool too. So you can take them for a test drive. Some people like this edit thing, right? You can try it, and it's a little window that's going to pop up here. Wherever it went, where did you go? Oh, there it is. So there it is, and it's just save, blah blah. Click on the thing, and it's relatively fast even drawing the pictures across the connection. So if you like to click and drool, maybe this is the one for you. I mean, if it's too hard to learn Control X, Control S, Control X, Control C, yeah, maybe you can use this one. This isn't going to do the nice little indentations of your stuff for you. You have to manually do that, but it is going to highlight the colors of the stuff. So you can try edit. There's tons of other ones you can give a test drive to. So go to this file that's in the handouts. Some people like this little nano thing. It's a really minimal um, type of deal, but whatever turns on. Nano doesn't do the X window stuff, so it's a lot quicker. It's just the text stuff, and the exit is Control X, and to save something is Control O, and then you just type a bunch of stuff and whatever. It's going to highlight. I think it'll highlight the C syntax. Maybe not. Yeah, no syntax highlighting, but whatever. Try that one. There's one called Joe. Some people like that. Anyway, test drive some of these. Try it on for size. Kick the tires. Drive it around the block. See which ones you like. Find something. But you need to learn how to use an editor remotely over on Schofield, because all of your project code that you're going to be doing has to execute on Schofield in order to contact grading server demons that are going to be running over there, that grade the thing and immediately tell you, okay, if this was your last version, this is the score you would get. So the way all that's set up, you're going to be running your code over there on Schofield. So you can edit on your local machine and then SCP it up to one of the Linux pool, and then from there SCP it over to the Schofield machine. But every time you change the file, you got to do 2 copies from one machine to another, which is a real pain to avoid learning Control X, Control S, Control X, Control C. Right. So have fun with your lab. I'm going to do my office hours at 2 today, 2 to 3. And so drop in. We can talk about any of this stuff, or we can just go over how to use some of these editors and other things, just mechanics of using the system, whatever you want. So at 2 o'clock. So if I don't see you at 2, I will see you Wednesday morning. Any questions about anything before we go here? What was the command to log into Schofield? Well, let me just do that. If you go to one of the Linux machines, like this is logged into the Linux machine, and you type in SSH -P922, your login ID. If you want X Windows stuff forwarded down the tunnel, you got to do -Y. And then you put your login ID on Schofield at Schofield. You don't really need all the .cs www.edu crap, because it's in the same domain as the machine you're on. And then just give it your password, and you're on Schofield if you type the password right. And if you exit, you're back over logged out and on the Linux pool machine. If you exit out of it, you're blowing everything away and back down to your local machine. Anything else? Yeah, VI, is a VI versus Vim and all, installations. If you type VI, you're actually getting Vim. VI is just a pointer symbolic link that points at Vim, so you type VI on any of the lab machines or Schofield, you're gonna actually get the Vim, the more modern version of VI. Anything else? So, alright, have fun with your lab.